Somewhere in Wyoming right now, a nuclear reactor is being assembled in a factory, not poured into the ground over a decade by an army of construction workers, not permitted through 17 layers of federal bureaucracy over the course of 20 years, built in a factory on an assembly line like a car. When it's finished, it will fit inside a standard industrial building. It will generate enough electricity to power a small city. It will run for years without refueling. It will produce zero carbon emissions. And it will do something that wind farms and solar panels, for all their extraordinary progress, still cannot do reliably: generate power on demand around the clock, regardless of what the weather is doing. The companies building these reactors aren't fringe startups chasing venture capital fever dreams. They are backed by some of the most disciplined capital allocators on the planet: Google, Microsoft, Amazon, Meta. The same companies that built the data infrastructure the modern world runs on have quietly concluded that the energy grid we have cannot support the world they are building, and they have decided to fund an entirely different kind of nuclear power to fix that problem. These devices are called small modular reactors. The industry calls them SMRs. And the fact that you probably haven't heard much about them, despite billions of dollars flowing into their development right now, is itself a story worth telling. Before we go further, if this is the kind of buried, consequential engineering story you want more of, hit like and subscribe to Lost Tech Vault. We cover the technologies reshaping civilization that the mainstream conversation consistently underestimates. This one might be the most urgent we've ever touched. To understand why big tech is going nuclear, you need to understand what AI actually costs, not in dollars, but in watts. A single query to a large language model consumes somewhere between 10 and 100 times the electricity of a standard Google search, depending on the model's size and the complexity of the task. That gap sounds manageable until you scale it. Google processes approximately 8.5 billion searches per day. As AI-powered responses replace or supplement a growing fraction of those queries, the energy math changes dramatically and quickly. Goldman Sachs published an analysis estimating that data center electricity demand in the United States alone will increase by 160% by 2030. The International Energy Agency projects that global data centers will consume more electricity by the end of this decade than the entire country of Japan does today. To put that in concrete terms, every major AI model you interact with lives inside a data center. That data center requires not just power, but guaranteed, uninterruptible power, the kind that cannot go offline because a cloud passed over a solar panel or because the wind dropped below threshold. The kind of power utilities call firm. And the uncomfortable truth the industry has been wrestling with quietly for several years is that firm, clean, scalable power at the density AI infrastructure requires does not currently exist at sufficient scale anywhere on the grid. Renewables can be clean, they can be cheap, but they are not always on. And battery storage, for all its rapid improvement, still cannot bridge the gap between intermittent generation and the kind of always-on baseload that a data center drawing hundreds of megawatts requires around the clock, every day for decades. This is the problem that sent Microsoft, Google, Amazon, and Meta's infrastructure teams back to nuclear physics. Nuclear power itself is not a new idea. The first commercial nuclear reactor to generate electricity for a public grid came online in the United Kingdom in 1956. By the 1970s, nuclear was being heralded as the energy source that would make electricity too cheap to meter. France built an entire national grid around it. The United States was on track to do the same. Then 3 Mile Island happened in 1979. Chernobyl followed in 1986, Fukushima in 2011. And with each accident, public trust in nuclear power collapsed in a new wave. Regulatory requirements multiplied, and the economics of large-scale nuclear construction became increasingly punishing. The most recent large nuclear plant completed in the United States, the Vogtle expansion in Georgia, took 16 years to build and came in at approximately $35 billion, more than double its original cost estimate. The sheer scale of gigawatt-class reactor construction, combined with the regulatory complexity, supply chain fragmentation, and one-off FEIC engineering required for each installation, had turned nuclear power into one of the most financially hazardous infrastructure projects a utility could undertake. The industry needed a fundamentally different approach, and the answer, it turned out, had been hiding in the United States Navy for 70 years. Nuclear-powered submarines and aircraft carriers have operated safely and continuously since the 1950s. The reactors that power them are small, self-contained, and engineered to operate in extraordinarily demanding conditions, underwater, at sea, in combat environments without large support infrastructure and without catastrophic failures. The US Nautilus, the world's first nuclear-powered submarine, completed a 60,000-mile voyage without refueling. These naval reactors are a mature, proven technology with a safety record that the civilian nuclear industry has never come close to matching. The foundational insight behind the Small Modular Reactor, or SMR movement, is straightforward. Take the engineering philosophy of naval reactors: compact, modular, factory-built, passively safe, and adapt it for civilian power generation. Where a conventional large-scale reactor generates between 1,000 and 1,600 megawatts of electricity and requires a purpose-built facility the size of a small industrial complex. A small modular reactor is defined as a design that generates 300 megawatts or less per unit. That ceiling is deliberate. It is the threshold below which factory fabrication becomes practical, transportation by road or rail becomes feasible, and site preparation costs drop dramatically. The most advanced SMR design currently moving through the Nuclear Regulatory Commission's approval process in the United States is the NuScale Voyager reactor, which generates 77 megawatts per module and can be deployed in banks of up to 12 units. Each module is approximately 65 feet tall and 9 feet in diameter, small enough to be manufactured in a controlled factory environment and shipped to site as a finished unit. But the design that has attracted the most concentrated attention from the technology industry is being built by a company called TerraPower, founded by Bill Gates in 2006, and now under active construction in Kemmerer, Wyoming. TerraPower's Natrium reactor is a 345 megawatt sodium-cooled fast reactor with an integrated thermal storage system. It uses liquid sodium rather than water as its coolant, which means it operates at atmospheric pressure rather than the high pressure conditions that drove the failure modes at 3 Mile Island and Fukushima. A reactor that operates at atmospheric pressure cannot suffer a pressure-driven rupture. The passive safety case is built into the physics, not bolted on through additional systems. The Natrium design also incorporates a molten salt thermal storage tank that can absorb excess heat when power demand is low and discharge it to boost electrical output when demand spikes, a feature that allows the plant to follow grid load dynamically in a way that conventional nuclear reactors cannot. It is, in effect, a nuclear plant with a built-in battery. The technology industry's commitment to this sector has moved well beyond letters of intent and exploratory conversations. Microsoft signed a 20-year power purchase agreement with Constellation Energy to restart Unit 1 of the 3 Mile Island nuclear facility. That unit was not involved in the 1979 accident, and it was shut down purely for economic reasons in 2019. The plant is now being refurbished, and it is expected to return to service, supplying power directly to Microsoft's data center operations. Google signed an agreement with Kairos Power to purchase electricity from a fleet of SMR, which are small modular reactors, with the first unit targeted for deployment before the end of this decade. It is the first corporate power purchase agreement for SMR-generated electricity ever executed. Amazon's investment arm has backed multiple nuclear energy companies simultaneously, including X-Energy, which is developing a pebble-bed reactor design that uses fuel embedded in graphite spheres and is physically incapable of achieving the kind of runaway chain reaction that produced Chernobyl's catastrophic meltdown. These are not philanthropic gestures or environmental, social, and governance optics. These are infrastructure procurement decisions made by companies that run some of the most cost-optimized operations in the history of capitalism. When Google locks in a 20-year power contract, it is because the financial modeling says that contract is the most economically rational way to secure the energy their systems will require. The honest accounting of where this technology stands, however, requires acknowledging what is still unproven at scale. No small modular reactor (SMR) design has yet completed construction and entered commercial operation in the Western world. NuScale's most advanced project, a planned installation in Idaho, was cancelled in 2023 after projected costs rose and anchor customers withdrew. The regulatory pathway, while improving, remains long and expensive. And the nuclear industry's history of cost overruns on novel designs is extensive enough that healthy skepticism about projected price points is entirely warranted. What has changed is the demand signal. For the first time since the 1970s, there are large, creditworthy customers actively willing to sign long-term contracts for nuclear-generated power. Not because they have been mandated to, not because it is fashionable, but because their engineering and infrastructure teams have concluded that no other technology solves their specific problem. The AI build-out is creating an energy demand that the existing grid cannot satisfy with existing clean technologies. The companies building that AI infrastructure have done the math. And the math keeps pointing to the same place. The Mini-Nuke is not a relic of Cold War ambition repurposed as a novelty. It is the calculated answer to a very modern question. How do you power a technology that never sleeps, with energy that never runs out, from a source that never emits? The engineers working in that Wyoming factory believe they already have the answer. The next few years will tell us whether they are right. If you want to see the other energy technologies that the AI industry is quietly betting on, including one that generates power from a temperature difference and has no moving parts whatsoever, subscribe to Lost Tech Vault and watch our next video now.